host this lecture today. And this is an announcement before the lecture begins about the postdoctoral council. There is a need for new members, and the postdoc council does a lot of work on behalf of postdocs to basically enhance the experience that you have here at the CfA. So if you're interested in joining the council, please contact Jennifer Yee. So I also want to note that this is a hybrid colloquium, and so if the people who are on Zoom, if you want to ask a question, just raise your hand or put something in the chat, and we have someone who will be looking after those questions. Before I introduce today's speaker, I would like to acknowledge the Clay Fellowship. Landon and Lavinia Clay established the Clay Postdoctoral Fellowship in 2000 to encourage and celebrate the observatory's outstanding researchers displaying significant promise in theory, observation, instrumentation, and/or laboratory experiments. It is my understanding that the Clay's son, Thomas Clay, is attending today virtually. Thomas is continuing his family's legacy in supporting CFA science by serving on the SAO Advisory Board. He's been a board member since 2020. We'd like to welcome him and thank him for his support. So now to introduce our speaker, Dr. Julian Munoz is a Clay postdoctoral fellow and will present today's lecture. He's a theorist working on understanding dark matter and its connection to the formation of the first galaxies. He did his undergraduate studies in his hometown of Madrid and obtained his PhD from Johns Hopkins University in 2017. Before joining the CFA, Julian was a postdoctoral fellow in the Harvard Physics Department. The title of his talk today is Cosmic Dawn, the Next Frontier in Cosmology. So let's welcome our speaker.
Thank you, Nancy. So thank you for coming to the room or attending virtually. And I want to before start really thank the Clay family for the fellowship, for the support, especially for the support during the pandemic, which has been much more needed. So if Thomas or anyone else, the family is watching or watching later, thank you very much. Yeah, so we're talking about Cosmic Dawn, which is the thing I've been focusing my research since I moved to the CFA, which is the epoch of the first structure formation. And I'm going to tell you how we'll become the next frontier in cosmology and what we can learn from it. And let me start by showing you a cute, let's see if this works. Yes, a cute simulation, of a structure formation in our universe by the illustrious group, which is actually hosted here at Harvard by Lars and other collaborators. And in these type of simulations, you can see a structure forming at the largest scales in the universe with filaments, galaxies, clusters, all beautiful things. And these simulations have been extremely successful predicting the large-scale structure of our universe today. But under the hood in these simulations, there are actually two assumptions that are important, and as of now, we don't understand fully. The first is that the gas that we see, the matter that is visible, it lives in the potential well of dark matter. We don't know what this dark matter is, but we know that it's fundamental for the structure formation in our universe. Also, we know the structure formation is hierarchical, forms from the smallest things all the way to the largest. And of course, what we see today tend to be very big galaxies, and when you rewind the clock, we don't know how the first structures formed the universe. And these are two open questions in astrophysics that are interrelated and for which we don't have an answer yet. So these are the frontier, what we know about cosmology. We don't know what dark matter is made of. We know that it forms the scaffolding of the large-scale structure. As I said, we need its gravity. And we see it all the way from the largest scales of the universe, hundreds of megaparsec, the CMB, and we even see it within galaxies. And that's actually how we first discovered dark matter. Vera Rubin looked at rotation curves of galaxies near the Milky Way. And by Kepler's law, the rotation of the galaxy is telling you how much mass there is. So when Vera Rubin looked around, she saw that the velocity of the galaxies has a very large value, whereas what you see, which is gas and stars, tend to be well below. So you need an extra component, and we've appreciated that this is dark matter. So we know what it is. We know what gravity does, but we actually don't know what it is. And dark matter is not only important for the dynamics of galaxies, it's also important for their formation. As I said, the galaxies we see today were formed out of smaller components earlier on, and when you go to the smallest galaxies in the early universe, these are formed out of very small scale clumping, very small scale homogeneities. And we don't know what dark matter is doing at these scales. So these two questions are related. The formation of the first galaxies can tell us about dark matter, and we need to understand dark matter to understand the first galaxies. Finally, as a sort of bonus question, we don't know what drives cosmic expansion. We know the universe is expanding. We know near us expands at an accelerated rate. This is what we call dark energy. But we don't know what's happening at any one of these eras. And this is one of the open questions in cosmology. So in my research, I use cosmological data to answer these questions. And in particular, I'm going to tell you about how we measure things in cosmology first to see how my research fits in. So what we do is we take maps of the sky. And of course, I'm sure you've seen maps of the cosmic microwave background, the CMB. It's the first light that was emitted when the universe first became neutral, and protons and electrons combined to neutral hydrogen, and all the photons that were, for the first time, freely able to travel, made it to today in these beautiful maps of the CMB that you see here. Now, the CMB has given us a lot of information, but it's not the only map of the universe. As the universe expands, so the CMB was emitted about 400,000 years to the Big Bang, so redshift 1000, if you're familiar with redshift, which most of you are. As the universe expands, the tiny gravitational fluctuations that gave rise to the hot and cold spots started to grow under their own gravity. And about 100 million years after the Big Bang, these tiny fluctuations first became large enough to host galaxies. At this time, they emitted light, the first light of the universe, and we call this epoch the cosmic dawn. And this allows us to see the universe from 21 centimeters, this spin-flip line of hydrogen. So they will give us new maps of the universe from this era of cosmic dawn up until the hydrogen is reionized, which is at about redshift 5 or so a billion years, where the hydrogen will finally separate electrons and protons. There will be no more 21 centimeter transitions. And of course, as galaxies keep evolving, keep getting bigger, emitting more photons, you will get to today. And you will see the whole beautiful universe that we see near us, with galaxies, clusters, supernovae, fantastic astrophysics. But from this whole picture that I've drawn here, really we only understand the beginning and the end. In the beginning, we have the CMB. We have very, very precise analytical calculations, and we have very clear data from satellites and ground-based experiments to compare against. And here in the light universe, we have, as I said, a plethora of observables that have made us, have allowed us to make progress. But if you push towards earlier times here, the situation starts to get less and less clear. Nevertheless, these two sites have become the pillars of modern day cosmology. And almost everything that we know about cosmology comes from data in these two sites. For instance, we don't know this dark matter, but we don't know what dark matter is. And despite how powerful these data are, it's not clear they're going to give us the answer. We could spend the next 50 years understanding the two sites better and better, and we might still not know. Well, the two sites seem to be telling us that dark matter is cold and collisionless, which is to say that it clusters at all scales. But we haven't seen all the scales. Here's a map of the fluctuation scales that we've seen in the universe versus cosmic time. So in the top left, you get the CMB, large scales, early times. Then you get the Lasker structure of the universe, which includes CMB lensing, includes galaxies, other lensing surveys, Lyman alpha forests, which is later times, relatively large scales. And you even have data from near-field cosmology, so studying the Milky Way, satellites, streams, which probes relatively smaller scales, but today, very close to today. If you have seen plots like this before, you're a cosmologist, you'll be used of thinking about halo masses and redshifts, so these are more natural units. But either way, the point of this plot is that there's a big gap in our knowledge. We don't know what's happening here. Small scales and early times. And this is where the first galaxies will form. They'll form out of very small scale fluctuations and early times during cosmic dawn. So we'll be able to understand this with astrophysical data soon. And different models of dark matter will give you different predictions for what's happening here. So mapping this is not only interesting out of theoretical curiosity, but to actually understand the nature of dark matter. As I said, for galaxy formation, the yellow region here, we have some understanding. For the first galaxies, we know very little about how galaxies form into dark matter halos. That's something we'll be able to answer. I talked about reionization, how the hydrogen in the universe slowly protons and electrons separate, and we don't have any more 21 centimeter. And this is the last major phase transition of our universe. Hydrogen will start cold and neutral at the beginning, hot and ionized at the end. But we don't know exactly how this happens. We don't have all the details yet, and this is something we'll be able to map. And finally, we don't know what drives cosmic expansion. Again, we know there's dark energy today. We know roughly what's happening at the CMB, but in between, there could be a lot of features in physics that we're missing. So this is the reason that I focus on this era, just because there's a lot that is unknown and we'll be able to map. So what I do is I try to make cosmic reionization into the pillars of cosmology. 2 new pillars to complement what we know from the CMB and the vascular structure. And there's a long road to make them at the same level of precision or understanding that we have, but that is the goal. So today in particular, I'll tell you about how using HERA or with 21 centimeter experiments, we can learn about dark matter and astrophysics. So the sort of outline of the rest of the talk is first I'll tell you about cosmic dawn, some basic of 21 centimeter, how it all works. Then I'll tell you about the question of dark matter and the first galaxies, how they're related, and we can learn about the 2 of them. And then I'll end talking about what is driving cosmic expansion. So let's begin. So the idea of 21 centimeter is that the CMB is a black body. And in fact, it's the most perfect black body we've measured in nature. The CMB, we know how many photons are emitted at each frequency. It peaks in the microwave, 160 gigahertz, give or take. And if you care about 21 centimeter photons, these are 1.4 gigahertz, it's all the way in the low frequency LSAT. So these are the photons that are emitted or absorbed in the singlet to triplet transition of hydrogen. So this is the part of the CMB spectrum we care about. Now, the trick is that the universe expands, the photons redshift. That's what we use the units of redshift. So their wavelengths get longer. So actually, this cartoon that I showed you, the CMB, looked like this when it was emitted. And as it moved towards us, it redshifted into the CMB, the black body that we see today. The trick, the reason we can learn 21 centimeter from this, is that not every photon from the CMB makes it to us. Some photons cross into a wavelength of 21 centimeter at some point, say at redshift 20, and they can get resonantly absorbed. And in that case, they just disappear. You see fewer photons on the other side. For this to happen, of course, you need the hydrogen to be out of equilibrium with the CMB. And this is where the galaxies come in. This out of equilibrium condition is telling you that there's more singlets in the hydrogen than triplets, than given what the CMB would predict. So you need the galaxies to produce what we call the Woodhouse field effect to actually give this condition. And if you want to hear more about how that works, please ask me more. But essentially, galaxies will produce this out of equilibrium condition, allow hydrogen to absorb the CMB, and therefore produce absorption. So in this cartoon that I showed you, what you will get is the CMB redshifts, and at some point you get a dip. And this dip occurs exactly at 1.4 gigahertz, at 21 centimeter wavelength or frequency. Now if this is redshift 20, say, when you keep evolving this to today, these will keep moving to the left. So by looking at the CMB spectrum and looking at this dip, you can go ahead and measure the temperature and density of hydrogen at this point, redshift 20. So what I've told you in this cartoon, in a bit more detail, is looking at the low frequency part of the CMB, is giving us information about hydrogen in the IGM. So in particular, each frequency of the CMB spectrum corresponds to a particular redshift by the 21 centimeter transition. And if you go and measure the intensity of the CMB, which is this black line, and you see departures from it, you can tell if any of the CMB photons have been absorbed by hydrogen. So the frequency information encodes the cosmic time. And what my experimental colleagues do is they go and measure this black line, and if they see fewer photons, then they measure absorption. And how deep this absorption is gives us information about the hydrogen. I'll talk more about that. If the hydrogen was very hot, it would just populate the triplet, so you would just get emission on top of the CMB. And you would get something like this. And how far the intensity is from the CMB prediction is what we call the 21 centimeter brightness temperature, T21. So this is not your usual thermal temperature. If it's positive, you get emission, but it can be negative, in which case you get absorption against the CMB. You get fewer photons. So this T21 is just linearly proportional to how many photons I'm winning or losing. And because that's what my experimental colleagues report, that's the quantity I'll be using through the talk. Okay, so far, it's all very cartoony, very hand wavy. Let me actually show you a simulation for what this P21 looks like in our universe. And it looks a lot like these cartoon simulations, but before I tell you more about the details of why it looks this way, let me say that this, of course, is what happens to the average CMB, the CMB coming to us on average. But our universe is very homogeneous. Different directions of the sky look very different. So you can actually build maps of this quantity. So if you look at different parts of the sky, you will look different values. So in particular, if you look at a particular line of sight, you will get something like this. So the signal will be slightly different. And the frequency gives us the redshift. And the angle in the sky gives us the position. So you can do this for one line of sight. You can point your telescope to a different point, get a different line of sight in principle, and build 3D maps like this. So this is the beauty of the 21 centimeter, that you can map our universe tomographically from the cosmic dawn to the epoch of organization. So now let me tell you actually what's happening in this plot from beginning to end. So at the left, we have the earlier times. At the beginning, there was nothing. This is redshift 35 before the first galaxies formed. So the signal is white on the top, which means nothing, or near zero. This is the global signal, which is the average. Now, as the first galaxies form, they produce a Wilson field effect. They bring the hydrogen out of equilibrium, and they start to create absorption. And you can see the islands of blue in the top, or you can see here, this becoming negative. Now, eventually, stellar remnants from the first galaxies are the more likely culprit. They heat up the intergalactic medium. And we believe it's stellar remnants because we believe it to be X-rays, in which case the curve will go up, and the gas will get heated. You see the islands of red on the top. And eventually, the whole thing will become red. And then you start seeing the islands of white. Those are bubbles of reionization. That's the hydrogen being reionized, and when electrons and protons separate, there's no more hyperfine structures, so no more 21 centimeter, and the signal will slowly go to zero. You get white on the top. So this is the overall structure of how the cosmic dawn reionization occurs. But there is a particular simulation, which I'll say, it was run with a code called 21CMFast, which Andrew Messinger in the audience developed, and I've collaborated with. These type of simulations allow us to predict this signal, but we don't know the values of all of these parameters. We don't know a lot about the first galaxies, and measuring 21 centimeters will allow us to understand their properties. So this is all very broad, very general, so let me give you a particular example. The way we can learn is by looking at this trough, this absorption part in cosmic dawn, because the depth of this absorption depends on the gas temperature, and when it occurs depends on structure formation, how structure forms. And in particular, both these things are very dependent on the properties of dark matter, as well as what the first galaxies are doing. So just by looking at this trough, we can actually learn about both the first galaxies and dark matter. So, okay, so far, it's all very theoretical simulations. How do you measure this? The first way to measure is by looking at the global signal, which is just the average across the sky. It's like a CMB monoplot. And it is extremely challenging to do in practice. That's because in addition to this global signal, this cosmic thing you want to see, you're seeing foregrounds from the galaxy. You're in the 50 to 100 megahertz range, and if you do radio astronomy, you know there's a lot of synchrotron from electrons in our galaxy. So you have to be able to subtract that. And there's about a 10 to the 3, 10 to the 4 larger signal. So it's very, very challenging. Nevertheless, some experiments are trying to do this. One of them, called EDGES, has a claim for detection. But I'll mention that Lincoln Greenhill here leads LIDA, which is also doing this. But this EDGES experiment, just to give you an idea, it's a very small scale experiment. This is what it looks like. It's about a few meters in size, and it's a very small crew of about 5 to 10 people. And they claimed the first detection of this signal, which in timing looked kind of like the models that I showed you, like cosmic dawn, redshift 17, but it was much, much deeper, which implies that the gas was much colder than what I showed you. And in fact, it was colder than is allowed in the standard model. So this first detection is harder to square with an understanding of astrophysics. Some folks claim it could be foregrounds. Some other folks have recently claimed to be systematics, because the Saras group, another independent group, has not been able to confirm it yet. All I'll say about this is that it could be that dark matter is interacting and cooling down the gas. So this gives us a new way, a new arena to understand dark matter that is independent of other laboratory experiments. Thankfully, I'm not going to say much more about the global signal because we have a better way of measuring this, which is by using the 21 centimeter fluctuations. And this is very much like in the case of the CMB, right? We have hot and cold spots in the CMB. Here we have hot and cold spots. But now we have 3D maps. We have tomographic information. This is targeted by interferometers like HERA, MWA, LOFAR. And in particular, I want to talk about HERA, the hydrogen epoch organization array. And to give you an idea of the scale compared to edges, this is what HERA looks like. It's 350 antennas, each of them 14 meters in diameter. The group is order 100 people. This is a much, much bigger investment. And you need it because you're trying to measure differences, like interferometry, so you need more antennas, you need more sensitivity. But this allows you to do one good thing, at least, which is that you can get rid of the foregrounds. Because when you measure the 3D signal, you measure fluctuation on the line of sight, fluctuations perpendicular. Foregrounds don't occupy the whole space. Foregrounds are very smooth spectrum. So if you were to do the Fourier transform of the signal in the foregrounds, you get different things. So let me illustrate this. This is what the power spectrum would look like, where K on the line of sight is on the y-axis. So this is the Fourier transform of the line of sight. This is the Fourier transform of angles in the sky. Foregrounds, in principle, should only live in low wave numbers on the line of sight because they're spectrally smooth. In reality, they end up occupying things below the black line because the antenna is chromatic, so the response is not the same at all frequencies. But they're contained to this region below the black line. So foregrounds live here, in this thing we call the wedge, and the cosmic signal lives everywhere. So in particular, if you look outside of this wedge, you can get pure cosmic signal and no foregrounds. And this is not just like a simulation or a theory. This is actual data from the paper experiment, which is a precursor to HERA. So our hope is to only use this data outside of the wedge and to measure the real cosmic signal. And this means we have to throw away most of our data, order 99% of it. But the 1% we keep is foreground free. And I'll say this because I know a lot of folks here think about these sort of questions. If you have ways of digging deeper into the wedge, please reach out. Because this means we're a factor of 100 off in sensitivity. If we can even get a tiny bit into the wedge, that can really get us to detecting the signal faster. So yeah, so we'll keep the foreground free part. We'll be very conservative. And even with this, we can still get results. So this is how the field has progressed over the last years. So these are limits on the power spectrum of 21 centimeters, so the Fourier transform of the signal versus cosmic time. And you can see how from like 2014, 2017 to today, the limits have been getting better and better. Now there is a log plot, so there's still, there's still a little off of where we want to be. But what I want to point out is that HERA has now the best upper limits during reionization. So in particular, this green arrow here and that there. And even though they're still high, these first limits only use about 20 nights of data and only 50 antennas out of the 350. Once the whole array is connected and data is processed, we definitely expect to get to these theory curves over here. But even from these first upper limits, we can do science. So I'll tell you a little bit about that. So one of the things that theory predictions have is they have very hot gas. They assume the gas has been heated by X-rays, etc. If the gas was not heated, the predictions would be much higher because the signal would be deeper. So at some point, if you lower the temperature of the gas, you will collide with these limits. You will be pulled out. So we can use the HERA data to understand the temperature of the IGM. Now within the HERA collaboration, there's been 3 theory groups which independently derive limits on the temperature of the gas using this data. And I was in one of them. And this is a way to show what we got. So these are the limits on the temperature of the gas versus cosmic time. So these are the 2 limits from the 2 bands that HERA has measured. And to give you a reference, the black line is the adiabatic cooling limit. So the black line is what you get if the gas was just slowly cooling down as the universe expands and nothing happened to it whatsoever. So you see this, they're roughly on this ballpark. But from each of these limits, we can learn something interesting. So from the first one, I mentioned edges as a teaser before. Edges needs the gas to be colder than adiabatic, colder than allowed by this most boring standard scenario. And one way to square edges with cosmology is to make the gas colder by interacting with dark matter. So you get something like the red line here. This red line would be ruled out by this first Hera data point. So it's telling you that something, if this is right, something has to happen between this edges data point and Hera. Now, of course, what we would like to do is to get the same sort of constraints all the way up here, redshift 17, which the data is being collected. We're working on it now. From the other data point, we're slightly before adiabatic, which is to say this has to be at least a little bit of heating happening in the universe. And as I said, we expect heating to come from X-rays. So you can actually translate this limit into some amount of X-ray luminosity per star formation rate in the universe. And this one of the first ways that we're collecting evidence that there were high mass X-ray binaries, and these high mass X-ray binaries at redshift 20 or redshift 10 were different than the local ones. And if you want to hear more details, please reach out. But until we have a detection, we'll not be able to explicitly say what the first X-ray sources were, but we're getting to the point of starting to put interesting limits. So, okay, if you want to hear what's next, we're working on the next data release, which is going to have 5 times more data on these bands. So we're going to be able to improve dramatically. And I say 5, it's 5-ish. You can see it takes, not all the antennas work all the time, so there's flagging. And of course, the thing that I'm very interested in is the cosmic dawn, the redshift 17 signal, and actually testing dark matter models by using Hera data, comparing against edges. And even from just upper limits, we'll be able to make progress both in the X-ray regime and comparing dark matter and comparing against edges. Any questions about this so far? Might as well stop asking questions. Yes?
So to have sensitive enough observations, Hera is strongly optimized to work around 500 million years. Is the sensitivity anticipated to be adequate to work around 200 million years or less?
Good question. Yeah, the original Hera was supposed to be 100 to 200 megahertz, as you know, so reionization up to, like, say, here-ish. They have the new Vivaldi feeds, which cover down to 50 megahertz. In theory, it gets to redshift 27, so like somewhere here. The sensitivity gets harder because the forograms get stronger, but when you do just the estimates of the sensitivity, it should be sensitive enough. And if edges was right, the signal would be a factor of 2 deeper in the global signal, at least, so a factor of 4 deeper in the power spectrum. So it should be 4 times easier. So it should be easier to rule out edges, and it might be slightly challenging to detect the standard cosmic signal. But we have to first rule out edges, and that should be easier. Yes?
So you showed edges with just this one little box.
Yeah.
Is there a reason you can't just make a few more of them to have a stronger detection?
The problem is the systematics. If you make a bunch of experiments, they're all the same, they might share the systematics.
But I mean, has anyone done a deeper version of?
Lincoln would know better, but I think, so something Edges has done is like the mid-band experiment, which is same but slightly smaller, and that means you move to higher frequencies. So a lot of the things you should with resonances or whatever, you would deal with that if you had a higher frequency experiment. Because if there was like a resonance in the experiment, it would shift. But a lot of the global signal experiments are not sensitivity limited. Like if you were to do the estimate, it just should detect the signal in like 14, I think it's 14 days, 15 days of data. So really systematic limited, which, yes?
You made some comment in passing on this plot saying that this would suggest that the high mass X-ray binaries in the early universe are different than local. Can you elaborate a little bit?
I can say a few more words. One of the things, we have a plot in the Hera paper where the amount of X-ray luminosity you get per star formation rate has, given what we know, take the luminosity functions from Hubble to extrapolate all these things, is slightly higher than what you get for local metallicity. So it's a question of metallicity. And you get slightly, where we are is slightly on the tail of the distribution. So the Hera data is telling us that maybe we need the X-ray luminosity to be slightly larger. which means less metallicity, so there's less winds and less mass loss in other ways. But it's a very, very indirect way, as you can imagine, of proving this. But it's one of the few ways we have on Redshift 10. So I don't know if there's, yeah. Yeah, we can chat more. And again, Andre is the expert on this X-ray stuff, so yeah, we can chat more. Very good. So let's talk about dark matter. So I'm going to show you a simulation. This is from the Ethos collaboration, and they simulate different dark matter models that have different dark matter properties, like dark matter self interactions, dark matter masses, and they simulate things like the Milky Way. So on the top left, you get the standard cold dark matter, the boring thing. Clusters at all scales. There's tiny dots, there's big dots, and the big blob in the center is the halo where the Milky Way would live. All these different Ethos models have different couplings, different properties, like fundamental particle properties, and they look very different. And this is one of the ways that cosmology has an unfair advantage when looking at dark matter, because we don't need to produce it in the lab. We don't need to actually make it. It's everywhere. We just need to study how it clusters. But all these type of studies have typically been done in the local universe. So, like, right here, this is a Milky Way-like halo. But everything that is to the right of this black line is deeply nonlinear. It's things that have collapsed and have formed structures. And they've given us a lot of information, but they've also been, it's complicated to analyze at times. For instance, when the subhalos fall into the Milky Way, they can get tidally stripped. So looking at the profiles might not have all the information that was pristine in the initial conditions. So what we would like to do is probe the same time of modes, the same time of tiny galaxies, not when they fall into the Milky Way and be processed, but at earlier times, when they're first forming as individual galaxies in the field. And that's what 21 centimeter will allow us to do. It will allow us to map the formation of the first structures. And the way it does so is by noticing that for absorption to happen, you need these blue blobs, this Woodhausen field effect. So you need first galaxies. And they will happen about redshift 25 here, this blob. And that's not a coincidence. That's because structure formation in our universe is hierarchical. Tiny things form first, and those grow into bigger things. So you from small things, they collapse into bigger halos and so on. So you can plot the typical halo mass that forms as a function of cosmic time, and it looks something like this black line. So it grows exponentially fast. And at some point, of course, you'll form things like the Milky Way, 10 to the 12 solar masses, or clusters of 10 to the 15 today. Now this is a cartoon, but it's telling you that structure formation happens in this order, but not every halo can host a galaxy. For a halo to host a galaxy, the potential has to be deep enough that the gas can actually come and collapse to the center and cool down. So you need a certain threshold to form galaxies, which is about 1 million solar masses. So this is for molecular cooling through H2 transitions. So when these two lines intersect, about redshift 25, is when the first galaxies will form, as promised. Now, in this model, the black line assumes dark matter is cold, so it clusters at all the scales. If dark matter was warm, self-interacting, fuzzy, or just has some interesting properties, you could suppress all the small-scale structure, all the small mass halos. And the first galaxies would form significantly later. You could also imagine going the other way. You could have extra power, extra clumping, and the line would extend to earlier times. So by studying the timing of cosmic dawn, we can tell the abundance of these halos. And therefore, we can tell what dark matter is doing at small scales. What I showed is that by doing these sort of studies and marginalizing over what we know about astrophysics, so things like the star-to-halo mass ratio, which I'll get back to in a second, these red regions where we can probe with 21 experiments like Hera. Now, the times that you cover are roughly cosmic dawn to reionization, and the point is you reach small scales at these molecular cooling halos, which are 1 million solar masses or so. So you can reach very, very tiny scales that are comparable to what we can see in the near field cosmology, studying stellar streams or studying satellites. And part of the interest of this is, of course, to probe the first galaxies, which I'll talk much more, but also to compare with the local universe and see if we get the same answer for dark matter. If in the local universe there was an excess, and there's been claimed over time an issue of missing satellites, which likely is baryonic physics, whatever is happening in the local universe also has to happen at high redshifts. Dark matter has to be the same. The systematics are very different, but dark matter has to be the same. So if in the local universe we find dark matter is warm, it also should be warm at redshift 10 or redshift 20. So So you can think of this as a way of getting different systematics in your data. Now, I mentioned that halo galaxy connection is one of the big uncertainties we have to look at, which I see as an opportunity to learn about galaxies. Because we know about galaxies in this yellow region, as I said, from Hubble data and closer to us from a lot of other data sets. But we don't know much about the first galaxies, which formed here in this region. In a way, what we've been able to do with things like Hubble is look at the tip of the iceberg, think this above the water, and only look at the brightest sources, but there's a whole lot of iceberg below that we're so far missing. And I'm going to give you an example of how 21 centimeter can help us with this. So here's a plot of a way to parameterize the halo galaxy connections, how you put galaxies into halos. On the y-axis is the stellar fraction, so the amount of mass that is in the form of stars, versus the mass of the host halo. And this yellow region, again, is what we've probed with Hubble with big arrow bars, but this is the region that we understand. So what you can do is you can take a toy model, where you just continue this curve. You say these are POP2, so second generation stars. I just continue this curve, and I cut it off at the atomic cooling threshold, and I assume the POP3 stars forming the first galaxies with no metallicity, which are molecular cooling. So again, this is a toy example. And then you can say, when I do this POP2, POP3 separation, what happens if I change the abundance of POP3 stars? And you can go and you can predict the entire 21 centimeter signal and see how it changes. That's what I'm going to show you. So here in purple is the standard signal that I've been showing you through the talk. And in blue is what you get when you have more POP3 stellar formation. So what you get essentially is the signal happens earlier. And especially here in the cosmic dawn era, early times, much less so reionization. At the reionization, these stars are subdominant. So by studying the timing of the signal, you can learn about the star-to-halo mass ratio at very, very small masses. But it is degenerate with a bunch of things. For example, the X-ray luminosity of the first galaxies will also change the timing and the amplitude of the signal, and we don't know it a priori. It's also degenerate with dark matter. For instance, in these ethos models that I showed you before, you have dark matter interactions with itself and dark matter interactions with dark radiation. So this is something that we parameterize in one of these papers. And if you make dark matter warmer, so you make something that looks more like warm dark matter rather than cold, the signal happens later, so it moves to the right here. And all the lines of the same color have different amounts of dark matter properties, so that the same mass, but different properties in the self-interactions. So you can actually also look for that, and you can see it's a whole zoo of things you can do to the signal. So what I've been working on with Charlotte Mason, who used to be a postdoc here and as faculty at Niels Bohr, is an efficient Fisher matrix formalism to deal with all the correlations and all the uncertainties without having to run and rerun Markov chain Monte Carlos every time. And to really find what are the properties of dark matter and galaxies we can find that are not degenerate with each other, which is going to be challenging, as you can see from these static plots. But all this has been very, very focused on Hera and 21 centimeter in the future. But you could ask, what can we say now? Hera's going to give us these beautiful 3D maps. We don't have them yet. Something we can do is look at the Hubble Space Telescope. And I'm not going to say a lot about this because I gave a luncheon talk a couple of weeks ago. But essentially, by looking at the luminosity functions that come from the deep fields, we can learn about galaxies in this regime, so up to about redshift 10. This is not the entire range that we care about, but it gives us the first way to go peer into the cosmic dawn. And here I mentor a student, Nash Shetty, on how to analyze this data on learning about dark matter, and we found that it covers this teal region over here. This data that we already have from Hubble, and within this teal region we found that it agrees with standard cold dark matter, perhaps as expected. But as you can see, this paves the way towards understanding cosmic dawn. And the overall guiding principle really is that whenever there's galaxies at early times, there has to be dark matter. So by studying the abundance of galaxies, we can compete and collaborate with the local universe to really understand what dark matter is made of. So I'm going to stop here to see if there's any questions still about this. Yes?
So you're seem to be assuming that all your hydrogen is living in halos. No?
No. Most of the hydrogen is in the IGM.
Oh, okay.
So in fact, a very, very small fraction is in galaxies. that is the fraction that will produce the photons that produce Wood-Hausen field effect, but most of the hydrogen is in the IG.
Okay. I guess I'm confused then about how you're going from the baryonic signal to the dark matter signal.
Good, because you need the galaxies. So let me go back to the slides. Because you need galaxies here, so you need some galaxies to be producing the 21 centimeter signal. We will almost like here. So the reason there's this blue patches here is because there's somewhere galaxies emitting photons. These galaxies have to live in dark matter halos. So if dark matter was warm, also interacting, those halos would not exist. And the baryons on their own wouldn't collapse because of silk damping. So you do need the galaxies, and therefore you need halos. Good. Oh yeah, sorry.
So in the plot you keep showing, by lambda, that's a co-moving size?
Correct, that's 1 over k.
Okay.
Yeah, that's correct. And I wanted to show k, but then large would go the other way. So I was trying to be, yeah. It's 1 over k. Yes?
Is there a simple reason why it's X-rays that are important for the heating and not just like from stars or accretion shocks? Or
There is, so thank you for bringing that up. It's because X-rays have very long Newton paths. X-rays have a small cross-section because of 1 over energy squared in the Compton. Like UV and visible light will heat near the galaxies, but not the overall IGM. So you need the X-rays to really travel a long distance. And it's really in the point something to 2 keV band. Things above 2 keV, the Newton path is longer than Hubble. So they just freely travel through the whole universe.
Thanks.
Yeah, so below 2 keV, above whatever they can escape, like 0.2, 0.5, we actually don't know. Good. Okay, so the last thing I'll talk about is about the expansion rate of the universe. And as a cosmologist, when I say expansion rate, I really mean what is the energy content of our universe? Because by GR, we know that the content of the universe determines how quickly it is expanding by geometry. So it's given by the Hubble expansion rate here is the sum of all the energy densities. And the Hubble expansion rate is the logarithmic growth rate as units of energy. So we can actually predict what this Hubble is, given what we know. You get a curve like this. This Hubble divided by what you will get in a matter-only universe, just so it's normalized to 1. But you see that it deviates both at early and late times from 1. At early times, what you get is radiation in the universe. You get photons, you get neutrinos, and they increase this higher than matter. Then you have an epoch of matter domination, and near us, you get dark energy, which makes expansion grow accelerated. But this is a beautiful theoretical curve with these 3 components, but we don't actually have measurements throughout all of this. And it's the topic of the talk. You can imagine we have measurements near today, we have measurements at the CFA. In particular, today the measurements come in 2 flavors. There's galaxy surveys, which things like Lambda Alpha Forest as well, which measure expansion rate through standard rulers. And there's standard candles, which directly measure the expansion rate by dimming. And we don't know what's happening in between. And in particular, it's interesting because the standard rulers and the standard candles disagree. Standard rulers, which are CMB and galaxies, give you a value of H0, which is the expansion rate today when you extrapolate. That is in disagreement with the standard candles, which are things like supernovae calibrated with Cepheids. And this H0 tension is at the 4 or 5 sigma level. So at the face of it, it's very serious. And we don't have a good explanation in terms of physics or systematics that can currently explain this 5 sigma tension. So I'm not going to try to explain it. What I'm going to say is that there's a new way to measure expansion rate, which is by putting a standard ruler during the dark ages, during cosmic dawn realization. And this is similar to what we do for the galaxies. Galaxies are complicated, but we make progress by using the baryon acoustic oscillations as a standard ruler. So I'm going to tell you how this works and how this relates to the cosmic dawn standard. So imagine that you have an overdensity in the universe, this very early universe, so redshift 10 to the 5. And this overdensity is overdensity in everything. Dark matter, baryons, photons, and neutrinos. Now I'm going to run this movie, which is actually made by Daniel. And you're going to see that because the photons have pressure, they're going to smooth away this density. They want to travel away from this overdensity. And they're going to drag the baryons with them. So the red and the blue are going to move away to the right until redshift 1000, at which point they're going to decouple, and the baryons in blue are going to get stuck. And the photons will keep traveling as the CMB to today. So this is telling you that the baryons have traveled some distance, which we call the sound horizon. It's about 150 megaparsec per moving. And that's only as far as they've been able to make. To give you an analogy, this is like throwing a stone into a lake, and you get ripples, you get waves. There's the fluctuation moving outward. But now, rather than letting this run forever, we're going to throw the stone into the lake, and then we're going to freeze the lake. So the baryons have only been allowed to travel some sound horizon, some 150 megaparsec. And this means that around every overdensity, there's a shell of baryons 150 megaparsec away that is also overdense. And this means the galaxies would tend to be correlated by this 150 megaparsec. And I don't need to know how they're made. I don't need to know what they're made of. This is just cosmology telling you things tend to be correlated by this distance. Now in all of this, I haven't talked about dark matter. Dark matter is just in the center, collapsing under its own gravity. So it's like slowly building over density. So this means there's different initial conditions between dark matter and baryons, which you can translate into a relative velocity. This velocity points inwards, because the dark matter is growing faster than the baryons. And it's exactly zero outside of this sound horizon, because at large scales, gravity is the same for dark matter and baryons, has to exactly cancel out. So these velocities are an excellent tracer of the acoustic physics of recombination, essentially because gravity cancels between dark matter and baryons. But let me give you more quantitatively a statement of this good tracer of acoustic physics. This is a correlation function of densities, so the 2-point function of real space. And you can see there's a big gravity component in dashed, and there's a bump at 150 megaparsec from the acoustic scale. So densities tend to be correlated by 150 megaparsec. But it's a relatively small bump. For the velocities, you get something like this. The gravity component is very small, and the acoustic part is huge. Because the acoustic physics is the main difference between the dark matter and the baryons. And these velocities are not just a curiosity. They actually affect the formation of the first structures. Regions of large velocity will form fewer galaxies, because galaxies are formed out of baryons gas falling to dark matter halos. If these two things have a velocity, they would just not collapse with each other. So you can see this here. I'm going to show you quickly a simulation. Top left is density, so initial conditions, essentially, and top right is a 21 centimeter simulation. And I'll be shocked if you were able to look at this and see baryon acoustic oscillations. It is a 1% effect. But now I'm going to show you what happens when you add the velocities. So here in the bottom left is the map of the velocities, which, as you can see, only has structure and acoustic scales, 150 megaparsec or so, because the gravity cancels. And these velocities affect the formation of the first structures, and therefore the 21 centimeter signal. So you can actually, even by eye, kind of see that regions of high velocity are bluer here, because there's fewer galaxies and therefore fewer X-rays. So this means that the signal in 21 centimeter, in it, has hidden a map of velocities. And therefore, by looking at the 21 centimeter signal, we can see wiggles, like acoustic oscillations, and we have a standard ruler. So I showed that by using this, we can measure they're called velocity-induced acoustic oscillations. They give us a new standard ruler, and we can measure the expansion rate of the universe to about 2% precision with Hera. That's what we expect. Whether it's 2, 1, or 4% will depend on how good the data is. The point is, we're going to have a new standard ruler to measure expansion rate independently of astrophysics. And it's going to be in this region of cosmic dawn reionization where we have no other measurements. So there could be dragons hidden here, and this will allow us to unearth these dragons. So I'm going to finish here, and then I'll take more questions. So in this talk, I've told you about how in cosmology, we've measured the universe around us by measuring glass structure and things like that, as well as the CMB, which is a slice of the universe really far. And this really gives us a lot of information. We've made a lot of progress by doing this. But there's still a lot of questions for which we don't have answers, like dark matter, dark energy, and so on. Thankfully, what you can see from this is that we have not observed most of the universe yet. A lot of it is in between these two eras, and we have so far very little information on it. Thankfully, we'll soon be able to map these epochs of cosmic dawn reionization by using 21 centimeter data. And also, I briefly mentioned Hubble Space Telescope, but of course James Webb will be able to push deeper into the cosmic dawn. So there's a lot of excitement over the next decade to understand this epoch in between. And I've told you how in my work, I use the new data from these eras to learn about cosmology and astrophysics. In particular, I focus on two questions. The first is, what is dark matter and how did it form the first structures? And the second is, what drives the cosmic expansion? For the first, I've told you about how I measured the small-scale structure of dark matter by using 21 centimeter and space telescopes, and how this can tell us about galaxy formation in the first galaxies, as well as the particle properties of dark matter, if it clusters, it's warm or fuzzy, or anything else. I've also told you about how I developed a new standard ruler, which is called velocity-induced acoustic oscillations, or VAOs, that measure the expansion rate halfway between us and the CMB. And the hope is to use these probes to really unearth the dark sector of our universe, dark matter and dark energy, and to finally understand what they're made of. Thanks.
Do we have more questions from the audience? Josh?
What sets this 150 megaparsec scale?
Good. That is the...
Given how little we understand dark matter, I don't understand. Is this,
Good. This dark matter plays very little role in the 150 megaparsec. This is the integral of the sound speed of baryons from initial times to recombination. So what dark matter can do is it can change the length, like when recombination happens. So it can change matter radiation quality. But that is just the overall abundance of dark matter. So really this is baryonic physics. This is coupling of photons to baryons and just the sound speed of baryons, which is all well controlled. Now you can change this, and what's one of the ways you can address the H0 tension is by making this smaller. But you need to introduce new physics. For example, you can make recombination happen earlier. So I think Misha, one of the graduates here, working with Daniel, has worked on by doing primordial magnetic fields. You can move this to the left, and then recombination happens earlier, and you can partially address the H0 tension. But you don't need to know what dark matter is made of to predict 150. Otherwise, yeah, it's really hard. Yes?
Tony?
How much does all this depend on the rest mass of neutrinos?
All this meaning everything that I've Good. One by one. So the H0 thing, not a lot. So this here, in fact, can help you because neutrinos tend, for 0.05 eV, will become non-relativistic at redshift 30, 20. So here you might actually see this light dip when the neutrinos go from radiation to matter. But that's like a 1% effect. So like, maybe in 20 years, this data will be good enough that we can measure this dip. But so for the expansion rate, that's something we can model really well. As you know, that doesn't change very much.
But that is a way of getting at that place where in your main plot there you have the wiggly line and break 3 orders of magnitude.
Oh yeah,
Between 10 to the 5 and 10 to the 8 is
Yes.
3 orders of magnitude, and
Yeah.
whereas the rest of the plot's only 2 orders of magnitude.
Yes. I don't know if we have any probe to directly measure the small scales at the CMB time. The neutrinos affect these large scales the most, right? The free streaming scale of neutrinos would be on the order of like tens, 100 megaparsec. So very large scales. Everything that I've described, like Hera and HST, tend to happen below the free streaming, so K larger than K free streaming, in which case the neutrinos just give you an overall offset that you can, in principle, constrain from the CMB. You can put a limit on the neutrino masses from the CMB. It would be good to know if you can use these with the CMB, combine them to get leverage to measure small and large scales together and get neutrino masses. But I don't think we're going to be at the percent level precision needed for that anytime soon. Like we're more on the discovery space, 10% error bars here. Upper limits for now, so 10% error bars.
Do we have any questions online? No. Martin?
Yeah, there's been quite a lot of talk from people like Joe Silk and Jack Birds about putting an interferometer on the far side of the moon to cut down the interference from the radio RFI. Is that a limiting factor, in fact?
I would need to check with experimental colleagues. I don't think so, because there's very clear flagging which frequencies are thrown away. That's true for the cosmic dawn. If you want to go earlier to dark ages, it absolutely is. The atmosphere is a big problem when you go to lower frequencies. So actually, one of my first papers in grad school was on the dark side of the moon, 21 centimeters. And it was on measuring non-Gaussianities, measuring the bispectrum, like 3-point functions. It would be one of the few ways to really get enough modes to get to the slow roll prediction, which is very, very small non-Gaussianity. So that would be on this, like what Tony called the wiggly line here. But that is very, very futuristic. You need a lot of antennas, and you need to put them on the moon, both of which are hard, I hear.
Right?
I think it's important not to leave without understanding what a VOA is, and I went by a little bit fast. So I think what you're doing is you're mapping the magnitude of the velocity difference between dark matter and baryons, the lower left there?
Yes, this is the magnitude, correct.
Okay, and you're saying as you go along a line of sights, those velocity differences will imprint themselves as wiggles on your spectrum on each line of sight?
You can think of it as T21 is going to be a bias tracer of the velocities.
Okay.
And this bias is a parameter that you don't care about, but the power spectrum of this will follow the power spectrum of velocities. And it's important that there's no cross terms with densities to first order. And that's because the velocity is as you said, a module, is velocity square root. So if you were to put that in a 2-point function with densities, it cancels out. Like it doesn't correlate to first order with densities.
Okay, that's not obvious at all to me, but
Okay, we can work it out. But the point is that
Yeah.
21 centimeter power spectrum will have a term that is proportional to the power spectrum of this. And this is the Fourier transform of this huge bump.
yeah, okay, that's cool.
So it's just a bias tracer of this thing. And this is only true at high redshifts. Because the velocities over time redshift away, and the galaxies get larger. So that you have to compare the velocity with the virial velocity of galaxies. So the virial velocity keeps getting larger, and the relative velocity keeps getting smaller. So this only matters for the first galaxy.
So it's a clean thing at high redshift.
Correct.
It wouldn't be a big mess.
People try to look for this in the BAO today, and they argue it's like a 0.3, 0.5% error on the regular BAO. But that's a tiny correction. But a high redshift is much larger than the regular BAO. It's an order 1 wiggle in a second.
So you're basically saying you can ignore the density because this is so much bigger at high
Correct.
redshift.
Correct.
That's great. Okay, yeah, I didn't understand that before.
I'm glad you
That's great.
Any more questions? Yeah?
So you said the foreground is many orders of magnitude bigger, but that's okay because it's very smooth.
Yes.
Is there any danger that it could be not smooth at that level?
Oh, absolutely, yes. There's different issues. So again, in an ideal world, you live below the black line, so everything is fine. In reality, there can be leakage. And part of the leakage can be calibration, part of the antennas are misplaced, and my experimental colleagues take a lot of effort on making sure there's no leakage. At the expense of sensitivity. Like, data's thrown away if we don't think it's if they don't think it's clean enough. So there's risk in that, but there's also a lot of mitigation. I'll say that I think in my experience, HERA is human power limited. Like, there's a lot of data, a lot of antennas that are built. All 350 are built. And they're connected, they're being connected to each other. The issue is really beating down the systematics and having people study and which data can be used, which data cannot. So we're in the regime of being very careful and needing people to test.
Yes, I mean, I get that for like the calibration stuff, but what about just like astrophysical signal?
Oh, so the reason we don't expect that is because you're such low frequencies, there's nothing that imprints structure other than the fluctuations of the universe. So there's like 50, 60 megahertz. If you were to emit synchrotron from anything, the relevant energy scale is the mass of the electron at G, like MeV, in your super low energy. So everything should be spectrally smooth. There's some wiggle, some error part, but I don't know.
Radio recombinations?
So there's spectral distortions from the CMB at the level of 10 to the minus 8 that people have calculated, like Jens, Kluba, and Yassin have. So these are well understood and very hard to observe. Especially when you go to lower frequencies, because free tends to rethermalize the CMB. So even if you did something, a recombination, free would tend to rethermalize to a black body.
Time for one last question?
Oh.
Do you have one on the, well, go ahead.
Yeah, one really quick point. I think Doug has a really nice code that is known to subtract out smooth foregrounds. Wink, wink. Anyways.
We gotta talk about that problem.
So you mentioned how we could see something dark matter being, like it should be the same at today in the near field cosmology, and the same at these high redshifts. How much of that, like if we do see that dark matter is behaving differently, how do you tell if that's baryons acting differently at the present day versus dark matter actually being different?
No, that's a good question. If you see the same, you have confidence. If you see something different, at least one of them is wrong. So that's something that we have to be careful, and we have to do a lot of careful modeling. And in the near field cosmology has been a lot of progress, as you know. From there's no missing satellites to, so there's missing satellites, there's none. And it's taking a lot of detailed theoretical work. That work is the work that I'm putting into the high redshift that other folks have as well. We so far don't have the detections to put like a data point. But once we have a data point, the work's not done. You still need, basically you're measuring a product of astrophysics and dark matter, and you want to understand the astrophysics better. So we're gonna get extra handles on it over time.
Cool, thanks.
Okay, so I think we should thank the speaker again.
Thank you all.
And,
This interferometric projection